All right, so we are going to continue talking about Hamilton circuits. That's what we started talking about last time at the very end. Hamilton circuits. This is different from Euler circuits. Remember, an Euler circuit in a graph is one which uses every edge without repeating any edges. A Hamilton circuit is the same but for vertices. So this uses every vertex, no repeats. All right? Uses every vertex without repeating any. That's called a Hamilton circuit. This is named after the mathematician Hamilton. Hamilton circuits, we're going to ask the same kinds of questions that we did for Euler circuits, which is like I show you a graph and you tell me does a Hamilton circuit exist or not, and can you find it? Those questions actually are quite a bit more difficult for Hamilton circuits than they are for Euler circuits. And I might as well tell you right now, there's no cute trick to tell if Hamilton circuits exist. Like with Euler circuits, it's all about just, are all the degrees even? And that's very easy to check if you're looking at a graph. But with Hamilton circuits, there is no similar easy thing to look for and immediately identify if there's a Hamilton circuit or not. So it's a little more interesting then, and that's what we're going to talk about the next few times. Hamilton circuits. So just a few, quick examples. We did some examples last time. How about this one here? Is there a Hamilton circuit or not? There is, although, like I said, there's no real cute trick for figuring it out. You just have to kind of look at it and figure it out by some sort of common sense. But here, I can make a Hamilton circuit. If I start over here, we can make one. I mean, there's more than one way to do it here, but here's one way to do it. You've got to make a circuit which hits every vertex once without revisiting any vertex. And that circuit does it. All right? I didn't use all the edges, but that doesn't matter. In a Hamilton circuit, we visit every vertex without repeating any vertices. Except, it's a circuit, so we end up where we started. But that doesn't count as repeating a vertex. All right? So this is a Hamilton circuit. This is a ham circ. All right. Hamilton circuits actually, from a practical point of view, when you're drawing them, they're much easier to draw than Euler circuits. Like there, I drew with my standard sort of slightly sloppy, curvy line. But I hope you agree. Actually, when you're drawing a Hamilton circuit, I'm just going to draw the same picture again. You might as well just do it like this. Right? With the Euler circuit, that is kind of ambiguous if you draw it that way, because the Euler circuit has to go across every edge and it loops back on itself many, many times. Hamilton circuit never does any of that. So actually, when I'm going to draw Hamilton circuits, I'm just going to draw it like that. I didn't put the arrow in there, but it's not ambiguous at all when I just draw that kind of thing. If you're just using, I have the two colors. If you're doing this with just a single pencil, which I assume most of you are, you can do something like this. Right? So on a test or a quiz or something, I would expect you, when you're drawing Hamilton circuits, to kind of draw it like that. If you want, you can draw the line with the arrows on it. That's fine. But this is good enough, right? The only thing I care about is it clear? Like, is it ambiguous or not? And this, if you're drawing an Euler circuit, this would be very ambiguous. But a Hamilton circuit doesn't revisit any vertices, so it turns out that this kind of picture works great for Hamilton circuits. All right, my main task for today is to talk about, if I show you a graph, can you tell me if there is a Hamilton circuit or not, and can you draw it in there? All right, let's see what we can do. So how to find Hamilton circuits, that's what I want to do today. Or show come on now. Or show there isn't one. All right, I have an awkward space after isn't. On a test or something, I will show you a graph, and it will be your idea to either find a Hamilton circuit in the graph or show that there isn't one. All right. So I got some simple examples and some more complicated examples. I got a cute handout here with some more complicated examples. Let's start easy though. So here is one. This is very simple. Graph like that. Is there a Hamilton circuit? Can you think of a way to make a Hamilton circuit here? You have to visit all the vertices. You do not need to use all the edges. Anybody see one just by looking at the graph? Can you see a way to visit all the vertices, not necessarily hitting all the edges? I see some people looking carefully. Anybody see how to do it? You might think, one idea. This is a bad idea, but one idea would be to go around the outside. That doesn't work because I missed the vertex in the middle. Anybody perhaps have a variation on that, which will make it work? You have to hit every vertex. You don't have to use every edge, though. Yeah? Yeah, do like this one. I agree. Do like this one, but don't use that diagonal. Instead of taking the diagonal, go in the middle and then back up the top. That is the way to do it. I think actually that's the only way to make a Hamilton circuit in this graph. All right? This hits every every vertex. It doesn't matter if you hit all the edges. So this one gets all the vertices. So this is a Hamilton circuit. All right, you have to get used to figuring these things out. It's very different from finding Euler circuits, so it takes a little bit of getting used to. I would like to make an obvious observation about this Hamilton circuit and any Hamilton circuit. So this is an obvious fact, but it turns out to be very useful. If you consider only the edges, which I'm using, only like the red edges here, only the chosen edges in the Hamilton circuit, each chosen edge meets every vertex. Sorry, this sentence is not going the way I wanted. What I want to say is these edges, where they meet the vertices, I wanted to say every vertex meets every, sorry about this. Every vertex meets two chosen edges. That's what I wanted to say. I said it backwards. Every vertex meets two chosen edges. Do you agree? Like this vertex right here has two red edges touching it. This vertex has two red edges touching it. All right, it has to be that way because the red edges are supposed to meet every vertex without ever revisiting them. If you visit the vertex once, that means one edge comes in, one edge goes out. So it's impossible to have three of these red edges meeting at a point because that means that the vertex is visited more than once. All right, so each vertex meets two chosen edges. All right, this is a simple, I said obvious fact, but it's actually very useful. In fact, it will allow you to build that Hamilton circuit even without just kind of looking and guessing. So without guessing, we use this fact about each vertex meets two chosen edges. Oops. I'm going to draw the same graph here, although I'm going to try and explain how you could do this without any guessing. Because, of course, just guessing answers is, it works sometimes, but it's not a great strategy. It would be best if we had some actual method. All right, here's what I look at. I'm going to look for degree 2 vertices. All right, I see one here, here, and here. Those are degree 2. That means there are only 2 edges. What that means is the edges that I choose in the Hamilton circuit, they must go through both of these edges. That's because I said before, every vertex must meet 2 chosen edges. If the degree is only 2, then you have to use those 2 edges in your Hamilton circuit. All right? So look for degree 2 vertices, and then those 2 edges must be used in any Hamilton circuit. It's because the Hamilton circuit has to have 2 edges which meet those vertices. And if those vertices have only 2 edges connecting them, then you got to use those 2 edges. So in this picture, I can immediately say those 2 edges must be used, also these 2, and also these 2. All right? With no guessing at all, you already know what most of the Hamilton circuit has to look like. All right? It has to involve those edges right here. All right? So we can fill in most of it without guessing. In this example, you know, sometimes there are no degree 2s, then you got a harder thing to work with. But we can fill in most of it with no guessing. Immediately. All right? Actually, this picture, we can even go further than that, still without any guessing. Check it out. If I look at this vertex now, I notice that there are already 2 chosen edges touching this vertex. That means I cannot use the 3rd edge right here. I'm going to just copy this picture so that it's clear what I'm saying from step to step. But here, say at this vertex on the left here, because I already have 2 red edges going through it, you cannot have more than 2, which means this edge cannot be used in my Hamilton circuit. All right? It's because every vertex can have, must have 2 red edges going through it. No more than 2, which means this one is off limits. For similar reasons, this one here is off limits. Yeah?
If it doesn't have a degree 3 anyways, or is that not a reason why are we not looking?
Well, this one has a degree 3.
And don't the other ones all have degree 2?
These ones have 2. Yeah, so the fact that this one has 2 means you have to use both of those edges. The fact that this one has 3 means 2 out of 3 of them are going to get used.
Oh.
But we've already used 2 of them, so the 3rd one cannot be used. All right? This is like a cute little puzzle. We're going to do a bunch of examples of this. It's a little tricky, but this edge right here, there's one other edge on the picture which I can rule out because of the same reason, and it's the one on the bottom here, right? Both of those edges now, they cannot be used because they would create a 3-way intersection, which is not allowed in a Hamilton circuit. So these ones, these can't be used since they make 3 red edges meet. I know you're not writing in red, but whatever if you're scribbling on them, they make 3 chosen edges. I'll use the word chosen to be a little more neutral. They make 3 chosen edges meet, right? And that's not allowed in a Hamilton circuit. And so those 2 edges are off limits, all right? I'm trying to finish the whole picture without any guessing, all right? Look at the middle vertex now. Here, this is a degree 4. Now 2 have to be used there. But I've already ruled out these 2 edges. That means the only choices at the middle vertex now is it must be this edge and that edge. And I will have completed the entire thing. So now I'll say now in the middle, only 2 edges remain. And so we have to use both of them. All right, and you end up with that same Hamilton circuit that we guessed before, but we figured it out without guessing anything. That's the point here. It's like that, right? No guessing, because I don't like guessing. I don't mind guessing. I don't like to rely on guessing, though, as a technique. All right? So this is the way that you can build Hamilton circuits. It's all about the fact, it's a simple fact, that every vertex has to meet two of the red edges, two of the chosen edges. All right? Here's another one. Let's try a bigger one. Oops. Look at that nice rectangle. I figured out how to make nice rectangles. All right, this is my graph, and it has one extra vertex right there. All right? Again, I want to try to find a Hamilton circuit in here without any guessing. You could probably, if you looked hard enough, just guess an answer if you spend enough time looking at it, but I'm not into that. Let's try to find a Hamilton circuit without guessing. So I'm going to begin, as we did in the previous example, identifying any degree 2 vertices. And on the degree 2s, you can immediately scribble in the two edges. So there's a degree 2 on the corners, right? And on those, I can immediately say I have to choose those two edges. All right. So I'm already kind of on my way here to building the Hamilton circuit. Are there any more degree 2 vertices? Actually, I see one more. Anybody agree? Yeah. Yeah, that sort of special one in the middle. That's a degree 2, which means I have to use those two edges. All right? Okay, so this is a good start. We begin by scribbling in the ones at the degree 2 vertices. Now you have to look a little bit more carefully. I would suggest looking at any edges which would make three-way intersections. Those are not allowed. I am considering something like this edge right here. If I were to scribble it in, it would make 3 meet over here, and that's not allowed. And so this edge I can rule out. Because if I were to use that edge on the left side of it, it would make a three-way intersection, and that's not allowed in a Hamilton circuit. And so that edge is not allowed. And for the same reason, the one on the other side, just sort of symmetrically opposite, that one also is not allowed. All right? All right. What else? Anybody see from here? Can we go anywhere? Yeah?
I don't know people.
Yes, I am.
At the top, just go down.
At the top, go down. Actually, I'm not
Like-
sure about that.
No.
Does it have to go down? I mean, it could go across here, right?
Yeah.
And then the rest of it maybe
bottom
could.
go.
I actually would like to try and do this without making any cute little guesses. Are there any other vertices where you see only 2 possible options? You got to choose those 2 options. That's what you should be looking for. Or are there some vertices where the 2 options have already been chosen, and so you can eliminate other ones? I actually see a vertex where there are only 2 allowable edges, and I should choose those 2 edges. Anybody see what I'm looking at? Do you see what I see? Do you hear what I hear? Check it out. I see right here, this vertex, it has 3 edges, but one has been ruled out. That means I must use the other 2. All right? This is a little tricky, but if you ever find yourself stuck, you should just go through the picture, look at each individual vertex, and ask yourself, is there any choice in the matter? And when I see this vertex here, I'll do a little narration here. Only 2 legal choices remain. And so you better choose those 2 choices. All right? And so I am going to choose the 2 vertical edges at that point. All right? It's this and that. Because I had X'd out the previous one, that means those two are the only ones to use. And then similarly, on the other side, for exactly the same reason, this vertex right here has 3 edges, but one has been X'd out, so I got to use the other 2. So I'm going to choose those 2. All right. Excellent. Are we done yet? Not quite, although at this point you can see the way to finish is just to connect across the top. Although, even if you don't want to use that cute little sort of common sense, I can say, for example, right here, I have already used 2 edges, which means this one is off limits. But once this one is off limits, it means I must use this one because right here I have 3 edges. I've used one, I've excluded the other one, so it must use this one also. So anyway, that's my final answer. All right, it's like a little puzzle or something. You go through the graph, and there's sort of alternating steps of you eliminate some edges, which means then you can say, then since that one was excluded, then I have to use this other one, and then since I had to use this other one, I can exclude this other one. That's the kind of thing that you gotta think about when you're doing these. All right. Any thoughts about that? All of this, what I've been saying so far, is about the degree being 2, right? All of this has to do with 2 chosen edges per vertex. All right? This is it's a very simple concept, but it's very powerful in terms of how far you can get using only this one principle. There is a second simple rule to use which can make this even more powerful. I will say another obvious observation. The first was that every vertex gets hit by 2 red edges. Another obvious observation is a Hamilton circuit has, I will just say, is one big circuit with no sub-circuits. This is, so what I mean by no sub-circuits is, like the example we just did, looked like this. That's one big circuit with no sub-circuits. So this one is, that's what it looks like, all right? You are not allowed in a Hamilton circuit, you can never have a sub-circuit. What I mean by that is something like this, which maybe goes around that guy and then comes back up here, all right? A sub-circuit meaning like a smaller circuit which is part of the larger circuit. That's not allowed. That is allowed in an Euler circuit, but not in a Hamilton circuit. Because in order to do this smaller one, you have to revisit several of these vertices, all right? So this thing right here, this little guy, that's a sub-circuit. And that's not allowed in a Hamilton circuit. In a Hamilton circuit, the only circuit that you should see on the whole picture is one big circuit. It has no other smaller circuits inside of it, all right? No sub-circuits allowed. So this whole thing, that's not a legal Hamilton circuit because it has those extra little sub-circuits, all right? So 2 big rules. I wrote rules with a U-E-L. 2 big rules about this is, the first one is what I said before. I'm just summarizing here. Each vertex meets 2 chosen edges. And the second rule is the chosen edges never make a subcircuit. And you can use those 2 rules together to find Hamilton circuits in all kinds of different example graphs. Let me just do one example which uses this sub-circuit thing. How about this example here? All right. So this is an example. Again, I want to find a Hamilton circuit without guessing. If you're going to guess, actually, you can just go around the outer edge. That's a Hamilton circuit. Although I want to see how we could figure that out without any guessing. So here, when I look at this, again, I could start with the degree 2 thing. I see two vertices which are degree 2. That's here and here. And that means we must use the edges there and also over here, right? So that's a good starting point. But actually, from this starting point, just looking at degrees, you can't go any further than that. You can go further, though, if you think about subcircuits. So I can ask myself, here I have these two red edges on the side here. That means this vertical edge right there is not allowed. Because if I were to use that edge also, it would make a subcircuit. It would make this little triangle closed off. And that is not allowed. So this edge right here is not allowed. That's because this one would make a subcircuit. And that is not allowed in a Hamilton circuit, all right? If I were to choose that one, it would make that closed up red triangle, and that's not allowed. That would be a smaller circuit, all right? The only circuit allowed is the big circuit, which includes everything. Okay, for the same exact reason, this one on the left side is also not allowed, because that also would make a smaller circuit. So these guys are not allowed. And now that means I have to use the one across the top and the one across the bottom. Those are the only edges which remain. So it must be, I'll just redraw it here. That means it has to be this. All right? Without guessing. Any thoughts about that? I got some examples, some big examples that I want you guys to try. Although can I just sort of summarize the tricks here? I don't know if all of this seems really obvious and easy to you. You will find when you try to do some big examples like this, it is a little tricky. You have to look very carefully at the graph to decide which edges you're going to use versus which edges you're going to exclude. So I'm going to try to summarize here. So this is all about building Hamilton circuits by, I will call this like edge choosing is sort of what I'm doing here. In each step, I am looking at the graph and deciding some of these edges I'm going to use, and also deciding some of these edges I'm going to exclude. So, for example, the first rule was about two edges meet each vertex. So, when you're doing that rule, for example, if I see something that's just like, if you actually see a vertex with only two edges, then you gotta use those two edges. So, in that case, you should actually choose both of those edges, right? If you see something like, if I see a vertex with three edges, but two of them are already chosen, then that means the third one cannot be chosen. So I can, if I see something like that, I can say this, right? If you see two edges which are already chosen, you can exclude any remaining edges at that vertex, all right? And then the other thing would be something like if I see maybe like this, where one is excluded and one is chosen already, then I can deduce from this picture that I have to use this other one, right? Because every vertex should have two chosen edges meeting it. And so in that situation, I can deduce that I have to use both of them, all right? This is the nuts and bolts of how you use that fact about every vertex has two chosen edges that meet it, all right? You can use this fact to decide which edges need to be used. You can also use this to exclude some edges and say they cannot be used, all right? And then the thing about the subcircuits is a little simpler. No subcircuits. So the way you would use that one No subcircuits is more like, you know, if I see something like this, where these two edges have already been chosen, it means you cannot use this one here, which would make a subcircuit connecting them. So this one, can I redraw that little diagram again? If I was already using those two, I may not use that one because that would create a subcircuit. All right? Just trying to give you the nuts and the bolts here. All right? So when you're doing this step by step, you want to just look across all the vertices in your picture and see if there are any that look like this, and that will allow you to put more information on your graph, either by choosing more edges or by ruling out some edges. All right, I got a couple big ones here. Let's try one that is easy to write on your paper, and then I have ones on a handout too, which are a little more complicated. All right, here's a little tic-tac-toe kind of thing. I'm going to insert some extra vertices like so. All right? Can we find a Hamilton circuit here? The first thing that you should do is choose edges at all the degree 2 vertices. This is how you can get started. So choose edges at the degree 2 verts. All right, so I am going to, that would be the corners here. Those are all degree 2s. And then also those extra points in the middle of those edges, those are also degree 2s. So we must use this edge, these edges, and that edges. Those edges. These and those. All right? So you should, this is always easy to do. You should begin by looking for degree 2s and choosing those edges. All right? Where do we go from here? Now it's a little less obvious. I'm going to copy this picture. I would not expect you to redraw the picture every time, but just for the sake of when I'm doing this here, if you're looking at these notes later on, I'm going to go step by step just because it's easy for me to duplicate the picture. I would like to look at this picture now. Can anybody say, are there any edges at this point which we can eliminate, like X out? Because you can eliminate anything which would make a subcircuit, or you could eliminate anything which makes a three-way intersection. Does anybody see any edges like that? I think there are many. What do you say?
Like 2 lines in the middle, but like on each side.
These guys.
Yeah.
Is that what you're saying? Yeah, I think this one we can eliminate. Why can't we use this one?
Just gonna make a subcircuit.
I don't think that makes a subcircuit. You can't use both of these would make a subcircuit here, but only one of them might not. Like this one by itself might be okay. Although this one I think is illegal because it would make 3 meet at the top if you use this edge. All right. So this one here we can eliminate. This one is because this would make a three-way at the top, which we don't like. Actually, it doesn't look like, I drew it wrong. It doesn't look like that. It would look like this, right? Right here. If you chose that edge, it would make a three-way intersection, which is not allowed. So that's why we exclude that one. Does anybody see any others which we should exclude? Yeah.
The top one.
The line across the top, yeah, for the same reason. It makes a three-way intersection right there. So you got to kind of look a little carefully. It may take you a little bit to look around. Basically, you want to look at each vertex and just make sure those kind of three-way things are never allowed to happen. So this also, same reason, I excluded this edge up here. All right? Any others we can exclude? You're looking for, yeah?
The one above the arrow.
Here?
Yeah.
Yeah, what's wrong with that one?
And
Yeah.
it would also make a subcircuit.
Yeah, right. This one right here also would make a three-way here, which is not allowed. And also, if you like, if that wasn't good enough for you, it would make a little subcircuit here if you used that edge. So that one also not allowed. All right. I think those are all of the simple exclusions we can make at this point. So all of these ones, these would make three-way intersections. That's why they are not allowed. All right, I'm going to redraw my picture just because it's getting a little busy here. Getting kind of hectic. Oh. All right, now what? I think we've X'd out all the ones that we can possibly X out. You should sort of alternate. Try to X out some and then try to draw in some. Are there any edges at this point which we can draw in? So what you should do at this point is look at each vertex and ask yourself, are there only two options remaining? And in that case, you got to take just the two options which remain. Anybody see one like that? Yeah. Yeah, this one here. Right. At this point, I have only two options remaining. There's the one I already chose and this one. Because that was X'd out, I have to choose this one now. So I choose that one. This is because, so that one right there, we only had one free edge, right? And so you got to take it. So choose it. All right? Anywhere else like that? Yeah. Yeah, the one on the far right, this one, if you look at this vertex here, there's only one edge available to choose. So I choose that one. So same with this, right? Any others? There may not be any others, I don't know. Yeah? Right here?
No, the first one.
This one?
Yeah, you can X out the line below it.
Yes. Yeah, so this was, maybe I'll redraw the picture again, but this was just adding some more edges. Now there are many more edges which we can X out, right? You got to kind of go back and forth with the choosing some edges and then eliminating some edges. And at this point, many edges can be eliminated. My eraser is too big. Many edges can be eliminated now. I think she said this one, no, this one, well, both of them actually. Both of these edges would make a three-way intersection right here. I've already chosen two, so I X that, I X that. Anywhere else, I also can X this one because that one would also make a three-way intersection right here. All right? Having X'd out those ones, now again, you can choose some that you weren't using before. I think at this point, since I X'd those out, right here I have only one option. I have to take this one here. Same goes right here. I have one chosen, one X. I must choose this one. And then I'm going to finish by choosing this one. All right? And that's it. Isn't that cute? It looks like a H. It's a Hamilton circuit with a H. Nobody expected that. All right? Any thoughts about that? It's like a cute little puzzle. Sometimes I think of trying to turn this into like a simple like phone app game or something where you get the graph and then you have to draw these lines and you X out some of them. It's kind of like Minesweeper or something like that. I feel like it's vaguely like that. I briefly thought about making something like that. I was going to call it Going Ham. I don't think anybody would play it. Maybe they would. I don't know. I would put some predatory in-app purchases, make the kids spend a lot of money without their parents' permission. All right, this is how we do it. Any questions about that? I got some more examples, but this is the way it goes. All right, let's try one on a handout. I'm going to do this first. These ones are just a little too big for you to copy down comfortably. Maybe we'll do the first one together, and then I will have you guys try the other ones. I put a few copies of each one on the paper. That's just in case you mess it up. Like I said, I won't expect you to like redraw it in steps. You should be able to do it all at once. All right, I have my version of this right here. Okay, so let's start with this guy here, this cute little guy. Find the Hamilton circuit, or explain to me why. Oh, you know what? I didn't mean to do this yet. Can we talk just for a few minutes before we do this? Sorry. Oh, I'm missing a page. It's all right. I remember what I was going to say. Forget about the paper just for a moment. The same ideas we can use the same tricks to show that no Hamilton circuit exists. And the way to do that is show why either a three-way intersection or subcircuit is unavoidable. As you're doing it, sometimes you will discover that a three-way intersection or a subcircuit is unavoidable. And that just means that it's impossible to make a Hamilton circuit. So here is an example like that. I got very simple examples here. How about this with a vertex in the middle? All right. And maybe just for fun, let's make it a little bigger. Sorry, I forgot my paper, which had the perfect example on it. But I'm going to put one there. Oops. All right, that's my final answer. This one has no Hamilton circuit. The way you would demonstrate that is proceed like you would before by, first of all, scribble in all the edges which have degree 2s. So you try to build a Hamilton circuit. Try to make one. I would begin by choosing these edges because that's a degree 2, that's a degree 2, so I have to choose those edges. This is a degree 2 here, so I have to choose those two edges. And then that vertex, that sort of extra vertex in the middle there makes a degree 2, and I have to choose these two. And then right away, you can see right here, I was forced into a three-way intersection. And that means, this is not because of some choice that I made. It has to be a three-way intersection there. That means automatically it's not possible to do a Hamilton circuit here. So I tried to make one. We were forced into a violation. So so my conclusion is this graph has no Hamilton circuit. Because any attempt to make a Hamilton circuit results in an automatic three-way intersection, which is not allowed. All right, that means it's not possible to have a Hamilton circuit in this graph. And there are some graphs which would force you into a subcircuit. For example, here is one like that. This is just a simple modification of a previous one, but I'm going to put an extra vertex right there. All right, this one, again, start by drawing in the degree 2s. And you will find you have to use that, and this, and also that and that. Although this one, I immediately made a subcircuit, which is also illegal. And so this one also has no Hamilton circuit, because here we're forced, really it's over here, right? Forced into a subcircuit. So no Hamilton circuit. All right. Any questions about that? I forgot to tell you my fun fact. Would you mind me sharing? This has nothing to do with anything, but over the little break, I was watching some of the World Cup soccer. Did you know that the World Cup The United States team goalkeeper is a former Stag, and I had him for 2 semesters of calculus, and he sat right there in this very room. Can you believe it? You were sitting in his seat. I saw an interview with him. He didn't mention me, but I recognized him. Although the interview, it was weird. Something cut out with my TV. It was a 10 seconds or so that I didn't catch. So I'm thinking maybe it was in there that he mentioned me. All right. So anyway, this is how you show there is no Hamilton circuit. You do the same old steps, but you end up being forced into a violation, and that means there cannot be a Hamilton circuit. Okay, let's look at the one on the paper then. Let's do the face guy all together, and then I'll let you guys try the other ones, and I'll walk around and see how you're doing. So with the face guy, like I said, I gave you a few copies just in case you mess it up. You should be able to do this just by looking at one of them. You begin by scribbling in the degree 2 vertices, and those ones I see, anywhere you see an extra vertex stuck in the middle of an edge, that's a degree 2, and so I must use this edge here, I must use this edge, and then I also see it around the sort of eyeballs of this guy, like so. All right. Any other degree 2 edges? Yeah, or vertices, I mean. The nose, yeah. Those sort of sharp corners of the nose are degree 2 vertices, and so I must use those edges there. All right? This is just considering the degree 2 vertices. All right? And I think that's it in terms of degree 2 vertices. Now, can we exclude any edges anywhere? You would like to exclude any edge which either makes a subcircuit or makes 3 meet. What do you think?
Top of the nose.
Yeah, the top of the nose here should be excluded. Why?
Because it would make a subcircuit.
Yeah, because that would make a subcircuit. It would close off the nose. So this is excluded. All right? I think maybe that's the only one in the picture which we can X out at this point. Given that we've excluded that one, are there ones that we can choose now? Yeah. Yeah, now you have to choose the edges on either side of the nose because it's a small picture, I know, but right here, this vertex has only one edge remaining, and I have to use 2 edges total. So I have to use this one here and this one here. All right? All right, I'm starting to feel pretty good about that. What can we do next? You are looking for any edges which you know you have to use, or also any edges which can be excluded at this point. I suppose you should look around the ones around. You always want to look sort of around the change that I just made. What further changes does that necessitate? Yeah? No? Yeah? Yeah, you cannot go across the top of the eye here because that would make a 3-way intersection right there. All right, so this is now disallowed. Similarly, on the other side, this is a symmetric picture, so we cannot use either of those 2. All right, it's because they would make 3 edges meet on the left end, the left end of this one. What else? You are again looking at, so look at these, maybe this vertex. Are there anywhere where you can say, perhaps there's only 2 options left, so I have to use those 2? Or maybe you disallow something because it could make a subcircuit? Anything like that? I just X'd out this one, so it might be a good idea to look at the vertex on the other end. And I think actually when I look at this vertex, I see 3 meeting. 1 has been X'd out. That means I must use the other 2, right? Every vertex is going to get 2 chosen. Since I've X'd this one out, I have to use the other 2. So that means I have to use this one and that one. Same goes on the other side of the picture. I have to use this one and that one. All right, what else? Yeah.
Well, you can't use the line below
I can't use the one here. That's correct, because I've already got 2 there. Although, actually, I was going to say something different. Anybody see there's something interesting about what we've done so far? Yeah. Yeah, actually, at this point, we have created a sub-circuit, right? This thing is a circuit, which is not the whole thing, right? That's a sub-circuit, which is not allowed, which means actually we can stop at this point and say, there is no Hamilton circuit because I just made a big sub-circuit. We made a sub-circuit. So no Hamilton circuit in this graph. We were forced into making a sub-circuit. All right? If you didn't notice that you had made a sub-circuit, you could continue, Xing out edges, choosing other edges. Probably you would make another 3-way intersection at some point or make another sub-circuit at some point. You would have figured it out eventually if you kept going. All right? That's how we do it. I would like for you all to try the other 2. You see one down here, and then there's one on the back also. So I'll tell you as a little hint. One of these, you can make a Hamilton circuit, and the other one is impossible. But I'll leave it to you to decide which is which. So see what you think. I will walk around and see how you're doing. Let me know how you feel.
person need to hit it.
Yes.
So that was a rule in itself.
Well, yeah, I mean, you have to choose 2 out of 3 privileges, but it's not really, at this point, I don't think you would say which 2 you can choose. It's going to get X. Yes, ham. That's an error.
Yeah. Yes.
Looks good. Let's chat about them. It looks like people are doing okay. So, I started off the first one just as you should. You should start by scribbling in the degree 2 vertices, and if you do that, to start with this one is you get this. And now you want to continue from there. I can X out a whole lot of them. Actually, from here, say if I look at the middle, I can X these other 2 because this is a 4-way intersection, but I've already chosen 2 of them. So I can put an X here and also here. I think maybe the simplest way, this one is impossible. As I walked around, everybody said this. And there are many different reasons why you can say it's impossible based on the steps that you took. At this point, maybe the quickest way I can finish this is from here now. I have 2 edges. One has been X'd. That means I have to use this one also. But that makes a subcircuit right here, right? So this is a subcircuit. Subcircuit. All right, and so this one has no Hamilton circuit. I hope that's what you said. Like I said, many people made their reasoning by, differently than the way that I just did it, but that's fine. Any questions about that one? All right, and this one here. Again, I will begin by choosing the degree 2 edges, or the edges which touch a degree 2 vertex. That's like these guys here, here, also here. I think maybe that's it. What else can we do? From now, we can scribble out any or X out any edges which would make 3-way intersections. So that would be this one right here would make a 3-way there. So I'm going to X this out. Also this one. No. Where else? I can also X out this one because that makes a subcircuit. Where did you go from there? I saw some people finish this one off. Can anybody say? I believe this one is possible. I saw some people figured it out.
On the left side, you go in down, back out to the left.
How did you determine that?
Oh, okay. Well then, I can just go based off of like where we are now.
Yeah. So
So you would have to go across on the bottom.
this one?
Yeah.
I don't know if I see that. I think at this point you may or may not use this edge.
Well,
Does anybody-
okay, at the top.
At the top?
At the top, you have to go down because then you won't be able to touch the vertices.
I don't know about that either. Can you go across? I'm trying to reason based on this picture so far. What can you? Yeah.
The right side, you have to connect.
Yeah, I think right here, this has to be used because at this vertex, I only have one more option at this point. It can be hard if you've already done this and try to come back to it and decide what step by step what you were thinking from one step to the next. If I use that edge, that means right here, in order to avoid a 3-way intersection, I should eliminate that edge here. So I X that out. What else now? I saw some people finish this, but maybe forgot. Anybody got thoughts about this? Yes.
For the top one, you can just directly connect it across.
Across the top? Oops. How do you know you have to do that?
Because if you go down any further, you would create a subcircuit.
Really?
Or
I-
throwaway one, because the one from below was already going up. Because for the one below, I went up further a little bit in the line, straight up from the bottom.
You went up here? Okay, yeah, if you had gone up here, you have to go across. Actually, you know what? I'm realizing this is a disaster. My picture, I just made this handout this morning because I figured rather than making them copy off the screen, I will hand it out to them. But I left something out of the handout. Can you forgive me about this? Actually, I believe from the picture at this point, it's not possible to make any further deductions. I meant to put a dot there, which changes everything. You can guess your way to the end from this picture before, but I meant for there to be a dot there. Sorry about that. Did I mention it's time to do the class evaluation form? I probably shouldn't mention that right now. I will mention that on a day when I don't make any foolish mistakes. Yeah, sorry about that. I meant to put a dot in the picture right there. So, now that I said that, can we proceed? We should have also chosen those two edges there, which means we can X out the other ones, which would make three-way intersections on the left side. So I X this, I X this. This picture may not be compatible with the answer that you wrote before if you guessed an answer. I try to make it so that you don't ever need to guess anything. You can make all of your choices by deductions. All right. Does anybody see from now, where can we choose edges? At this point? By the way, you might expect me to say something like this on a test. Rather than asking you to draw me the whole picture, I might draw you a picture sort of in progress, like give you one like this and ask you, from now, can you say exactly where you might have to use some edges or eliminate some edges? Anybody see any? Did you see? Yeah.
You're gonna have to use the line that wasn't an X added to on the square.
Yeah, here? Here?
Well, you have to make
Here?
like a thing there. I don't know how to like.
I got to make a thing. How about, I don't know if this is what you're trying to say, but how about at this vertex here, I have one X'd out, I got to use the other two. And similarly right here. Is that what he was saying? I don't know. Since this vertex had one X'd out, I got to use the other two. And also right here, there were two X'd out, I have to use the other two there. So this edge like that, all right? All right, I'm starting to feel better about this now. How about this edge right here? I think I can X that one out because that makes a subcircuit, right? If I were to use that edge, it would make a subcircuit. So I'm going to cross that one out. And for the same reason, this one. This edge right here also would have made a subcircuit. It would have made this little square. That's not allowed. Given that I've X'd those two out, I can now choose this edge here because there are only two options from this point. So I choose that one like so. How are we doing? Okay, I mean, now in order to avoid three ways, I think I have to go down here and across the top, and that'll do it. All right, sorry I messed up the point there, the dot. It matters. Without the dot, you can still do it, of course. Like this Hamilton circuit still works without the dot, but it was ambiguous without the dot. All right. Those are all the examples that I want to do. Can I, in our remaining 7 minutes, can I just start talking a little bit about what I want to talk about starting next time? All right, any questions about these examples, first of all? All right. I'm going back to my other notes here. All right. What we are going to talk about for maybe the remaining everything in the semester, maybe, I don't know if we're going to get through this all. I would like to talk specifically about Hamilton circuits in what are called complete graphs. Complete graphs is a special type of graph, which are very simple actually. We could have been talking about them all along, but here's the definition. A graph is called complete when any two vertices are connected by an edge. Most graphs are not like this, but if every two vertices have an edge between them, that's called a complete graph. So for example, here's an example of a complete graph. This is a graph of 4 vertices, and I will leave you to verify for yourself. It is true that every 2 vertices have an edge between them in this graph, all right? Like these 2 vertices have this diagonal edge. The other 2 have this weird outside edge like that, all right? That is a complete graph because every pair of vertices has an edge between it, all right? Or something like, here's a simpler one. Something like that, right? That's a complete graph because every 2 vertices have an edge between them. This is a complete graph of 4 vertices. This is a complete graph of 3 vertices. You could make a complete graph with 5 vertices. How about I would just sort of start with them in a circle, and then every vertex has to connect to every other vertex. So the one on top has to connect to all the other ones. The one on the right also has to connect to all the other ones. I'll just draw like that. These ones on the bottom have to connect. Everyone has to connect to every other one. And if you're using 5 vertices, it's got to look like that. This is a complete graph on 5 vertices. Actually, this is called the complete graph because there isn't another way that you can do this. You might draw it slightly differently, but every complete graph is going to be the same. There's only one way to do a complete graph on 5 vertices. And actually, there are special names for these. Not all that special. We call them K whatever. So the complete graph of 4 vertices is written as K4. The complete graph on 3 vertices is called K3. This is K5. All right? And so on. This is the complete graph. Let me just draw, just for fun. This would be K8. You have 8 vertices, and then just every one connects to every other one. There's a lot of edges in a complete graph, right? Did I say this would be fun? This is maybe bigger than I had intended to draw, but you get the idea. I think I drew in all the edges. This is K8. All right? That's the complete graph on 8 vertices. It has many, many edges in there. All right? What I want to talk about, it turns out to be very applicable in the real world, is finding Hamilton circuits in complete graphs. So maybe that'll do for today. That's what we'll start up next.